Every night, when darkness falls, you stand beneath a river of light that stretches across the sky. Ancient civilizations saw it as spilled milk, a path of souls, a celestial bridge. But what if I told you that this faint band of light is actually your view from inside something impossibly vast? You are not looking at the Milky Way. You are looking from within it, gazing at the inner walls of your cosmic home. For the next hour, we will step outside our familiar perspective and witness our galaxy as few ever imagine it. Come with me, and together we will see home as we have never seen it before. Let us begin by establishing where we are. If the universe were an ocean and galaxies were islands scattered across its vastness, then the Milky Way would be the island we were born upon. Our cosmic address is surprisingly specific. We exist in a galaxy containing somewhere between 200 and 400 billion stars, though the exact count remains one of astronomy's most challenging mysteries. This galaxy is not alone. It belongs to a small cluster we call the Local Group, containing more than 50 galaxies in total. But among all these celestial neighbors, the Milky Way is ours. It is the swirling disk of stars, gas, and dust that has been our home for as long as humanity has existed, and for billions of years before that. The galaxy we inhabit is ancient beyond our everyday comprehension. Current measurements suggest the Milky Way formed approximately 13 billion years ago, when the universe itself was still in its cosmic infancy. In those early epochs, smaller proto-galaxies collided and merged, their stellar populations mingling like drops of water combining into a larger pool. Over billions of years, these chaotic beginnings gradually organized into the elegant spiral structure we would recognize today. You and I are not just observers of this galaxy. We are products of it. Every atom in your body was forged in stellar furnaces that burned in this very galaxy, perhaps in previous generations of stars that lived and died billions of years before our sun even formed. When we look at our galaxy from our position within it, we see that band of light arching across the night sky. The ancient Greeks called it Galaxias Kyklos, the Milky Circle. The Romans simplified this to Via Lactea, the Milky Way. Nearly every culture that gazed upward created stories to explain this luminous pathway overhead. What none of them could have known is that they were seeing their own galaxy edge on, looking through the disk toward the crowded center. Imagine you are inside a vast Ferris wheel made of stars. When you look toward the hub, you see countless lights overlapping. When you look perpendicular to the wheel, you see far fewer stars. That is precisely what we experience every night. Understanding our place in the galaxy requires understanding scale, and the scales involved are truly staggering. The Milky Way measures roughly 100,000 light years from edge to edge. That means light itself, traveling at nearly 300,000 kilometers per second, would take 100,000 years to cross from one side of our galaxy to the other. To put this in perspective, the light you might see tonight from a star on the far side of the Milky Way began its journey before modern humans walked the Earth. We are not just looking at space when we gaze at the stars. We are looking back through time, witnessing light that has been traveling through the cosmos for longer than human civilization has existed. Our sun resides in what astronomers call the Orion Spur, a minor spiral arm situated between two major arms of the galaxy. We orbit the galactic center at a distance of approximately 26,000 light-years, placing us in the galactic suburbs rather than the densely packed downtown region. This position is neither random nor insignificant. The quiet neighborhood we inhabit has likely been crucial to the development of complex life on Earth. Here, far from the violent radiation and frequent supernova explosions that characterize the galactic center, our solar system has enjoyed billions of years of relative peace. This calm environment has allowed life to flourish, evolve, and eventually develop the capacity to contemplate its own cosmic home. As we prepare to explore our galaxy in greater detail, take a moment to absorb this fundamental truth. You are not separate from the Milky Way. You are made of it. The carbon in your cells, the iron in your blood, the calcium in your bones, all of these elements were created inside stars that called this galaxy home. Some of those stars lived and died before our sun was born, their remnants scattered into the cosmic clouds that would eventually collapse to form our solar system. In a very real sense, we are the Milky Way contemplating itself. We are the universe awakening to its own existence. And now, together, we will explore the magnificent structure of our cosmic home, from its blazing core to its invisible outer reaches. Before we venture deeper, let us acknowledge the tools that have allowed us to map our home. For most of human history, we could only observe the Milky Way from within, our view limited by dust and distance. But in recent decades, infrared and radio telescopes have pierced through obscuring clouds, revealing structures invisible to our eyes. Space telescopes have captured light from distant galaxies similar to our own, allowing us to infer what the Milky Way must look like from outside. Computer models, fed with billions of observations, have reconstructed the three-dimensional structure of our galaxy with remarkable precision. The journey we are about to undertake is one that our ancestors could only dream of, but we can now experience through the accumulated knowledge of countless astronomers and scientists who have dedicated their lives to understanding our cosmic home. Now we begin our journey into the structure itself. If you could somehow step outside the Milky Way and view it from a great distance, what would you see? The first thing to strike you would be the shape. The Milky Way is a barred spiral galaxy, one of the most common and beautiful architectures in the universe. Imagine a flat disk with a bright bulge at its center and graceful spiral arms winding outward from a central bar structure. This is not a solid object, but rather a dynamic system of billions of stars, each following its own orbit around the common center, their collective motion creating the patterns we observe. The entire structure rotates, though not like a rigid wheel. Different parts orbit at different speeds, creating the illusion of spiral arms that persist even as individual stars move through them. The disk of the Milky Way is remarkably thin compared to its diameter. While it stretches 100,000 light-years across, it is only about 1,000 light-years thick in most places. This creates a shape rather like a dinner plate or a flying disk. Within this thin disk reside the youngest and most vibrant stars, the vast clouds of gas and dust from which new stars continue to form, and the beautiful spiral arms that give our galaxy its characteristic appearance. If you could fly above or below the disk and look down upon it, you would see why spiral galaxies are considered among the most aesthetically pleasing structures in the cosmos. The arms glow with the blue light of young, massive stars and the red glow of emission nebulae, while darker dust lanes trace intricate patterns between the bright regions. At the very heart of this structure lies the galactic bulge, a dense, roughly spherical concentration of stars. This bulge spans about 10,000 light-years and contains some of the galaxy's oldest stars. These ancient suns formed when the Milky Way was young, and they have witnessed billions of years of galactic history. The stars here are packed much more densely than in our solar neighborhood. If Earth orbited a star in the galactic bulge, our night sky would be spectacular beyond imagination, with thousands of stars brighter than Venus visible on any clear evening. But we will explore this central region in much greater detail shortly. For now, simply appreciate that this bulge serves as the massive heart around which the entire galaxy revolves. Extending outward from the bulge is the distinctive bar structure that classifies the Milky Way as a barred spiral. This bar stretches approximately 27,000 light-years from end to end and acts as a cosmic highway, channeling gas and dust toward the central regions where it can fuel star formation. The bar is not permanent. Computer simulations suggest it formed relatively recently in galactic terms, perhaps only a few billion years ago, and may eventually dissolve as the galaxy continues to evolve. The gravitational influence of this bar shapes the orbits of stars throughout the inner galaxy, creating the complex patterns of motion that ultimately generate and maintain the spiral arm structure. Without the bar, the Milky Way would likely have a very different appearance and perhaps a very different history. The spiral arms themselves are perhaps the most iconic feature of galaxies like ours. The Milky Way has two major arms, the Perseus arm and the Scutum Centaurus arm, along with several minor arms including the Orion spur where we reside. These arms are not physical structures in the way a tree's branches are. Instead, they are density waves, regions where stars and gas are temporarily compressed as they orbit the galaxy. Think of them like traffic jams on a circular highway. The cars move through the jam, but the jam itself persists in roughly the same location. Similarly, stars enter a spiral arm, slow down slightly due to increased gravitational forces, then exit on the other side. The arm remains visible because at any given moment it contains more stars than the space between arms. The spiral arms are where the galaxy comes alive with star formation. Within these arms, giant molecular clouds, some containing millions of times the mass of our Sun, collapse under their own gravity to form new stars. The most massive of these young stars burn brilliantly but briefly, their intense ultraviolet radiation ionizing nearby gas and creating the glowing emission nebulae that paint the arms in shades of red and pink. These massive stars live fast and die young, exploding as supernovae within just a few million years. Their deaths compress nearby clouds, triggering new waves of star formation in a self-perpetuating cycle. This is why the spiral arms appear so bright and vibrant. They are the galactic nurseries, the maternity wards of the cosmos, where stellar birth is an ongoing, spectacular process. As we contemplate this grand architecture, we must acknowledge what we cannot see. Between the visible stars and nebulae stretches vast amounts of seemingly empty space. But this emptiness is an illusion. Thin clouds of gas, primarily hydrogen, fill the spaces between stars. Cosmic rays, high-energy particles accelerated by supernova explosions and other violent events, stream through the galaxy at nearly the speed of light. Magnetic fields thread through the disk, guiding the motion of charged particles and shaping the structure of nebulae. And pervading everything, invisible but essential, is dark matter. We will explore this mysterious substance in detail later, but for now, know that the beautiful visible structure we have been examining is merely the luminous surface of something far more massive and enigmatic that holds the entire galaxy together with its gravitational embrace. This, then, is the basic architecture of our home. A barred spiral galaxy, 100,000 light-years across, containing hundreds of billions of stars arranged in a thin rotating disk with graceful spiral arms. A dense central bulge of ancient stars surrounds a supermassive black hole at the very core. The entire visible structure is embedded in a vast spherical halo of dark matter that extends far beyond the visible stars. It is simultaneously elegant in its large-scale structure and almost infinitely complex in its details. Every cubic light-year contains wonders that would take lifetimes to fully appreciate. And we have only just begun our journey. Come with me now as we venture toward the blazing heart of the galaxy, the mysterious and powerful core that lies at the center of everything. We now descend toward the center of the Milky Way, toward a region so dense with stars and so energetic that it challenges our understanding of physics. The galactic core is both the literal and figurative heart of our galaxy. Here, in a region spanning just a few hundred light-years, resides more than 10% of the galaxy's total stellar mass. The gravitational forces are immense. The The radiation levels are lethal, and at the very center, lurking in absolute darkness, is an object so massive and dense that not even light can escape its grasp. This is Sagittarius. H. The supermassive black hole that serves as the anchor point for our entire galactic home. Let us approach with appropriate reverence and wonder. From Earth, we cannot see the galactic center in visible light. Vast clouds of dust lying along our line of sight absorb and scatter optical photons, rendering the core invisible to our eyes. But light is just one form of electromagnetic radiation, and the universe speaks to us in many wavelengths. Infrared radiation, with its longer wavelengths, can penetrate the dust. Radio waves pass through even more easily. X-rays generated by superheated gas reveal the most violent processes. By observing the galactic center in these different wavelengths, astronomers have pieced together an extraordinary picture of this exotic environment. What they have found is a place unlike anywhere else in the galaxy, a region where the rules that govern our quiet solar neighborhood no longer fully apply. The stars near the galactic center orbit at tremendous velocities. Some complete their orbits around Sagittarius X in just over a decade, reaching speeds of up to 5,000 kilometers per second, nearly 2% the speed of light. By carefully tracking the motions of these stars over many years, astronomers have been able to measure the mass of the central black hole with remarkable precision. Sagittarius contains approximately 4 million times the mass of our Sun, yet this enormous mass is compressed into a region smaller than the orbit of Mercury. This is the defining characteristic of a black hole. Not its darkness, not its gravitational pull, but the incredible density that results from compressing so much mass into so small a volume that the escape velocity exceeds the speed of light. What is it like to be a star orbiting so close to a supermassive black hole? The gravitational forces are so strong that the stars themselves are distorted, stretched slightly toward the black hole by tidal forces. The space around them is curved to such an extent that light does not travel in straight lines. Time itself flows at a different rate near the black hole than it does here in our solar neighborhood, running slightly slower due to the intense gravitational field. These are not abstract theoretical concepts, but real, measurable effects that have been confirmed through decades of careful observation. General relativity, Einstein's theory of gravity, predicted all of these phenomena, and the galactic center serves as a natural laboratory where we can watch relativity in action on a grand scale. Despite its tremendous mass, Sagittarius A is surprisingly quiet for a supermassive black hole. Many galaxies contain active galactic nuclei, where the central black hole is actively feeding on infalling material, generating more energy than all the stars in the galaxy combined. Our black hole, by contrast, is relatively dormant. It does occasionally feed when a gas cloud or unlucky star wanders too close, and when it does, telescopes across the electromagnetic spectrum observe bright flares of radiation. But most of the time, it simply sits at the galactic center, its gravity organizing the motion of everything around it, a dark heart pumping the orbital rhythm of hundreds of billions of stars. We should perhaps be grateful for its quiescence. An active galactic nucleus would make the central regions of the galaxy uninhabitable for planets like Earth, surrounding Sagittarius. ACE is a region of intense star formation known as the Central Molecular Zone. This is where some of the galaxy's most massive and luminous stars are born. The environment here is extreme. Gas clouds are heated to temperatures far higher than those in the outer galaxy, yet paradoxically, the density is also much higher, leading to the rapid formation of giant stars. Many of these stars are doomed to short lives. They will burn through their nuclear fuel in just a few million years, then explode as supernovae, enriching the galactic center with heavy elements and perhaps triggering new waves of star formation. It is a cycle of birth and death playing out at an accelerated pace, driven by the extreme conditions that exist so close to the supermassive black hole. Perhaps the most mysterious features emanating from the galactic center are the Fermi bubbles, vast lobes of high-energy gamma-ray emission extending 25,000 light-years above and below the galactic disk. These enormous structures, discovered only in 2010, may be the remnants of a period of intense activity from Sagittarius A several million years ago. Perhaps the black hole consumed a large amount of material in a relatively short time, driving powerful jets of matter and energy outward along the galaxy's rotational axis. These jets inflated the bubbles we see today, which now glow with the signature of particles accelerated to nearly the speed of light. The bubbles are a reminder that our galaxy has not always been as calm as it appears today, and that the galactic center harbors energies and processes that can affect the entire galactic disk. As we prepare to journey back outward from this intense region, take a moment to reflect on what the galactic center teaches us. Here, in a space that would fit comfortably inside the orbits of stars in our local neighborhood, are concentrated forces and energies that dwarf anything we experience in the calmer outer reaches of the galaxy. The presence of Sagittarius A is not incidental. Supermassive black holes appear to be fundamental components of large galaxies, and their growth and evolution is intimately connected to the growth and evolution of the galaxies themselves. In ways we are still working to understand, the black hole and the galaxy co-evolve, each shaping the other. The heart of our galaxy is both terrifying and essential, a reminder that beauty and danger are often intertwined in the cosmos. We now turn our attention to perhaps the most wondrous process occurring in the galaxy, the birth of new stars. Throughout the Milky Way, particularly in the spiral arms, vast clouds of gas and dust collapse under their own gravity to form stellar nurseries. These regions are among the most beautiful structures in the universe, combining physics and art in ways that leave even experienced astronomers awestruck. What does it mean for a star to be born? How does a diffuse cloud of gas spread across light years of space transform into a blazing sphere of nuclear fusion? For the next several minutes, we will explore this miraculous process, witnessing creation itself as it unfolds in slow motion across cosmic timescales. Star formation begins in giant molecular clouds, the largest structures in the galaxy. These clouds can span hundreds of light years and contain enough material to form millions of stars. They are composed primarily of hydrogen molecules, with a sprinkling of helium and trace amounts of heavier elements. The temperature within these clouds hovers just a few degrees above absolute zero, making them among the coldest places in the universe. They are dark. Very little light penetrates their depths. It is only when observed in infrared or radio wavelengths that we can peer inside these opaque cocoons and witness the early stages of stellar birth. Within these frigid, dark clouds, gravity is patiently at work, slowly pulling material together, setting the stage for ignition. The trigger for collapse can come from various sources. Sometimes the shock wave from a nearby supernova compresses part of the cloud. Sometimes the gravitational influence of a spiral density wave does the work. Other times, collisions between clouds provide the necessary compression. Once a region becomes dense enough, gravity takes over. The cloud begins to collapse, and as it collapses, it fragments into smaller clumps. Each clump continues to collapse independently, and within each collapsing clump, a protostar begins to form. This is not yet a star. The temperature and pressure at the core are not yet sufficient for nuclear fusion. But the object is heating up, glowing in infrared radiation and accumulating more and more mass from the surrounding cloud. A star is being born. As the protostar continues to accumulate mass, conservation of angular momentum causes it to spin faster. The material falling onto the protostar does not fall directly inward, but instead spirals in, forming a rotating disk of gas and dust around the growing star. This is an accretion disk, and it plays a crucial role not just in feeding the young star, but also in determining whether planets will eventually form. Within this disk, dust grains collide and stick together, gradually building up larger and larger particles. Meanwhile, the protostar at the center continues to contract and heat up. When the core temperature reaches about 10 million degrees, something extraordinary happens. Hydrogen nuclei begin to fuse into helium, releasing tremendous amounts of energy. At that moment, a star is truly born. The moment fusion ignites marks a dramatic transition. The new star generates powerful stellar winds that begin to blow away the remaining gas in its vicinity. The radiation pressure from the star's light pushes on dust grains, clearing out the immediate surroundings. Many young stars also generate powerful jets, beams of matter and energy that shoot outward along their rotational axes at tremendous speeds. These jets collide with surrounding material, creating glowing shock fronts called Herbig-Haro objects. Slowly, but even as one star clears away its birth material, other protostars continue to form in the surrounding cloud. Star formation is not a solitary event, but a collective process that can continue for millions of years within a single molecular cloud. One of the most iconic stellar nurseries in our galaxy is the Orion Nebula, visible to the naked eye as a fuzzy patch in the Sword of Orion. Just 1,500 light-years from Earth, it is close enough that we can study it in exquisite detail. The nebula is illuminated by a cluster of young, hot stars at its heart, known as the trapezium. These stars, born just a few million years ago, are so massive and so luminous that their ultraviolet radiation ionizes the surrounding gas, causing it to glow in beautiful shades of red, green, and blue. The Orion Nebula is not just beautiful. It is a laboratory where we can observe the entire process of star formation, from the densest protostellar cores to newly revealed young stars to the dispersing remnants of the original molecular cloud. Another spectacular region of star formation is the Eagle Nebula, home to the famous Pillars of Creation. These towering columns of gas and dust, each several light-years long, are being eroded by the ultraviolet radiation from nearby massive stars. Yet even as they are destroyed, they are sites of ongoing star formation. At the tips of the pillars, small, dense knots of material, called evaporating gaseous globules, resist the destructive radiation long enough for stars to finish forming within them. Eventually, these new stars will emerge from their pillars just as the pillars themselves are eroded away. It is a race between destruction and creation, and it illustrates a fundamental truth about star formation. The process is self-limiting. Massive stars form first, and their radiation and stellar winds eventually disperse the cloud, preventing further star formation. Every stellar nursery contains the seeds of its own destruction. As we reflect on the process of stellar birth, we must acknowledge its profound implications. Every star in the galaxy, including our Sun, formed through this process. The molecular cloud that gave birth to our solar system some 4.5 billion years ago was enriched with elements created in previous generations of stars. Without those earlier stars, without their deaths and the dispersal of their ashes into space, the cloud that formed our Sun would have contained only hydrogen and helium. There would have been no carbon, no oxygen, no iron, no silicon, no rocky planets, no possibility of life as we know it. The cycle of stellar birth and death is not just an astronomical curiosity. It is the mechanism by which the universe creates complexity, diversity, and eventually the conditions necessary for life. We are, quite literally, children of the stars, born from the ashes of stellar nurseries billions of years ago. Let us now explore the spiral arms in greater detail. These graceful structures, winding outward from the galactic center, define the appearance of our galaxy and play a crucial role in its evolution. We have already learned that spiral arms are density waves rather than fixed structures. But what does this really mean? How do these waves form and persist over billions of years? And what is it like to live within a spiral arm as our solar system does? For the next several minutes, we will journey along the length of these cosmic rivers, understanding their nature and appreciating their beauty. Come with me and let us trace the path of light and gravity that creates the Milky Way's most recognizable features. Imagine you are floating high above the galactic disk, watching it rotate. The disk does not rotate like a solid object. Stars closer to the center complete their orbits faster than stars farther out, just as inner planets in our solar system orbit the sun more quickly than outer planets. This differential rotation should, it would seem, wind up the spiral arms until they become tightly wrapped around the galactic center. Yet the arms persist for billions of years without becoming impossibly twisted. This is the winding problem, and its solution was one of the great triumphs of 20th century astrophysics. The answer lies in understanding that the spiral arms are not chains of stars moving together, but patterns through which stars pass, like cars moving through a traffic jam on a highway. The density wave theory explains how spiral arms form and persist. A spiral-shaped region of slightly higher gravity moves through the disk at a different speed than the stars themselves. As stars orbit the galaxy, they enter this higher density region, slow down slightly due to the increased gravitational pull, spend some time there, then exit and resume their normal orbital speed. Because many stars are simultaneously present in the density wave, that region appears brighter than its surroundings, creating the visible spiral arm. The wave itself rotates at a constant pattern speed, slower than the stars in the inner galaxy but faster than stars in the outer regions. This elegant mechanism allows spiral structure to persist indefinitely without winding up or dispersing. It is a pattern frozen in time, even though the individual stars creating the pattern are constantly changing. The spiral arms are not merely regions of higher stellar density. They are also where gas clouds are compressed, triggering the formation of new stars. This is why spiral arms are so visually striking. They are lit up not just by the random stars passing through, but by bright young stars that formed within the arm itself. The most massive of these stars, the brilliant blue giants, live for only a few million years, not long enough to move far from their birthplace before they die. Consequently, they remain within or near the spiral arms, illuminating them with their intense blue light. The arms also contain the glowing emission nebulae that mark sites of ongoing star formation, adding splashes of red and pink to the blue stellar light. This combination creates the breathtaking appearance we associate with spiral galaxies. The Milky Way's major arms have names that reflect the constellations they appear to pass through when viewed from Earth. The Scutum Centaurus arm, named for Scutum and Centaurus constellations, is one of the two primary arms. The Perseus arm, passing through Perseus constellation, is the other. Between these major structures lie several minor arms and spurs. Our solar system resides in the Orion spur, also called the Orion arm, a minor structure between the Perseus and Sagittarius arms. The fact that we live in a spur rather than a major arm may have implications for the development of life on Earth. Major arms experience more frequent supernova explosions and higher radiation levels. Our position in a quieter spur may have provided a more stable environment for life to evolve over billions of years. What is it like to pass through a spiral arm? Our solar system orbits the galactic center approximately once every 225 million years, a period sometimes called a galactic year. During this long orbit, we periodically enter and exit spiral arms. The last time Earth was in its current position relative to the galactic center, dinosaurs roamed the planet. The next time Earth returns to this position, 225 million years from now, the planet and its inhabitants, if any remain, will likely be unrecognizable. As we move through a spiral arm, the night sky slowly, over millions of years, becomes slightly richer with bright stars and visible nebulae. The rate of nearby supernova explosions increases somewhat. But these are subtle changes, nothing that would be noticeable on human timescales. The spiral arms affect the galaxy's large-scale evolution, but their influence on individual star systems is gentle. Some spiral galaxies, like the Whirlpool Galaxy or the Pinwheel Galaxy, display extremely well-defined, almost perfect spiral arms. The Milky Way's arms are less organized, somewhat more irregular. This is partly because we cannot easily observe our own galaxy's structure from outside, and partly because the Milky Way's arms are genuinely more chaotic than those of some other spirals. The central bar plays a role in this. Barred spirals tend to have somewhat less perfect arms than unbarred spirals. The bar channels gas inward, potentially disrupting the neat density wave patterns that would otherwise form. Yet this irregularity is part of what makes the Milky Way unique. Our galaxy is not a textbook spiral, perfect and idealized. It is a real galaxy, messy and complex, shaped by billions of years of evolution and countless gravitational interactions with its neighbors. As we prepare to move on from our exploration of the spiral arms, let us appreciate what they represent. These structures are not permanent features etched into the galaxy. They are waves, patterns, ephemeral in the cosmic sense, even though they persist for billions of years by human standards. They are where the galaxy renews itself, where gas is compressed into new stars, where the cycle of stellar birth and death plays out most actively. They are the mechanism by which galaxies like ours continue to shine brightly billions of years after their formation. Without spiral arms, the Milky Way would have exhausted its gas supply long ago, leaving only old, faint stars gradually fading into darkness. The spiral arms ensure that our galaxy remains vibrant, dynamic, and beautiful, a home worthy of life and consciousness. Now we return home, or at least to the general neighborhood we call home. After traversing the galaxy from its central black hole to its vast spiral arms, it is time to examine our own local environment in greater detail. The Sun resides in a region of the Milky Way that is remarkable, primarily for its unremarkability. We are far from the crowded galactic center, not in a major spiral arm, not in a particularly dense star cluster. We occupy a quiet suburb of the galaxy, and this quietness has profound implications. For the next several minutes, we will explore the local stellar neighborhood, the nearby stars that are our closest cosmic companions, and the peculiar bubble of rarefied gas that surrounds us. Welcome home. The Sun's nearest stellar neighbor is Proxima Centauri, a small red dwarf star lying just over 4 light-years away. Light from Proxima takes 4 years and 3 months to reach Earth, meaning we see it not as it is now, but as it was in the recent past. In the vast scale of the galaxy, 4 light-years is essentially next door. Yet in human terms, it represents an almost unimaginable gulf. The fastest spacecraft ever built would take over 70,000 years to reach Proxima Centauri. This illustrates a fundamental truth about our galactic neighborhood. Even the nearest stars are separated by distances so vast that interstellar travel remains, for now, firmly in the realm of science fiction. We are isolated not by the emptiness of space, but by its sheer scale. Within about 15 light-years of the Sun, there are approximately 60 star systems. Most of these are red dwarfs, small, cool stars that make up the majority of stars in the galaxy. A few are similar to our Sun. There are also several white dwarfs, the dense remnants of stars that have exhausted their nuclear fuel. What is notable about this stellar census is how empty our neighborhood truly is. Divided into a sphere 15 light-years in radius, these few dozen stars occupy a volume of over 14,000 cubic light-years. On average, each star system has hundreds of cubic light-years to itself. If the Sun were the size of a grain of sand, its nearest neighbor on this scale would be another grain of sand about 10 kilometers away. Space is not called space for nothing. It is overwhelmingly empty. Our solar system resides within a structure known as the local bubble or local cavity, a region about 300 light-years across where the interstellar medium is much thinner than average. This bubble was carved out by a series of supernova explosions that occurred in our region about 10 million years ago. These explosions swept away most of the gas and dust, creating a cavity of hot, tenuous plasma. We live inside this cavity, looking outward at the denser material that forms its walls. The local bubble has important consequences for our observations of the galaxy. Because the local interstellar medium is so thin, we can see farther and more clearly than we could if we were embedded in a typical region of the galactic disk. Our clear view of the cosmos is partly due to ancient supernovae that cleared the space around us. The Sun moves through the galaxy at a speed of about 220 kilometers per second relative to the local standard of rest. This motion is not random but follows our orbit around the galactic center. As we orbit, we also bob up and down through the galactic plane, completing one full oscillation roughly every 60 million years. Currently, we are very close to the galactic plane, but in about 30 million years, we will reach our maximum height above it before falling back down and crossing to the other side. These oscillations have been proposed as a factor in mass extinctions on Earth, though the evidence remains controversial. Each time we cross through the denser regions of the galactic plane, we may encounter more dust and possibly more comets, potentially increasing the rate of impacts on Earth. But this is speculation. What is certain is that our motion through the galaxy is complex, three-dimensional, and governed by the combined gravitational influence of hundreds of billions of stars. Among our stellar neighbors, a few stand out as particularly interesting or significant. Sirius, the brightest star in Earth's night sky, is just 8.5 light-years away, a blue-white star more than twice the mass of the Sun. Epsilon Eridani, 10 light-years distant, is a Sun-like star that may host a planetary system. Barnard's star, 6 light-years away, is a red dwarf moving through space faster than almost any other star, crossing the sky at a rate noticeable over human timescales. Tau Ceti, 12 light-years away, is another Sun-like star, slightly smaller and cooler than our own, potentially orbited by planets in its habitable zone. These nearby stars are not just points of light. They are worlds unto themselves, some perhaps with planets of their own, some perhaps even with conditions suitable for life. Our immediate cosmic neighborhood is rich with possibilities. What makes our location in the galaxy particularly favorable for life? Several factors stand out. We are far enough from the galactic center to avoid the intense radiation and frequent supernova explosions that characterize the inner galaxy. We are in a region where heavy elements, the building blocks of planets and life, are abundant enough to form rocky worlds, but not so abundant that planetary systems would be disrupted by excessive material. We are in a relatively stable orbit, not passing through spiral arms too frequently, and we exist in a period of galactic history when star formation has slowed from its early frenzy but has not yet ceased entirely. The galaxy is neither too young and chaotic nor too old and dying. It is in a mature phase, and we are in a mature location within it. This combination may not be unique, but it is certainly favorable. As we reflect on our neighborhood, we might feel a sense of both insignificance and privilege. The Sun is one of hundreds of billions of stars residing in an unremarkable location in an ordinary spiral galaxy. Nothing about our position is special or unique in any cosmic sense. Yet this very ordinariness may be precisely what has allowed life to flourish on Earth. The quiet stability of our location has given evolution billions of years to work, producing the extraordinary diversity of life we see around us and eventually consciousness itself. We are cosmically ordinary and biologically extraordinary, a product of the universe's tendency to create complexity given enough time and the right conditions. Our quiet galactic neighborhood is not the center of the universe, but it is the center of our universe, the place where matter became aware of itself. We now venture beyond the familiar disk of the Milky Way to explore a region that few contemplate, but which holds crucial clues to our galaxy's history. Surrounding the disk is a vast spherical halo containing globular clusters and individual stars that follow highly elliptical orbits. These are the galaxy's oldest inhabitants, relics from the epoch when the Milky Way was first forming. For the next several minutes, we will examine this stellar halo, understand its structure and composition, and learn what it tells us about our galaxy's past. Come with me now into deep time to meet the ancient guardians that have watched over our galaxy for more than 12 billion years. Globular clusters are among the most beautiful objects in the galaxy. Each cluster is a spherical collection of hundreds of thousands to millions of stars, all bound together by their mutual gravity. They orbit in the galactic halo, passing through the disk periodically but spending most of their time in the vast empty space above and below it. What makes globular clusters special is their age. These clusters formed very early in the galaxy's history, between 12 and 13 billion years ago. Their stars are among the oldest in the universe, born when the cosmos was less than 1 billion years old. By studying globular clusters, we can look back to the dawn of our galaxy, understanding what the Milky Way was like in its infancy. If you could stand on a planet orbiting a star in the core of a globular cluster, your night sky would be spectacular beyond imagination. Thousands of stars would be bright enough to cast shadows. The sky would never be truly dark. The nearest stars would be separated by distances measured in light weeks or light months rather than light years. This proximity, while visually stunning, makes globular cluster cores dangerous places for planetary systems. Close encounters between stars are not uncommon. Such encounters can strip away planets or fling them into interstellar space. This may be why we have not yet found evidence of planets within globular clusters. The dynamic environment is simply too chaotic for stable planetary systems to survive for billions of years. The stars in globular clusters are metal poor in astronomical terms. Here, metal means any element heavier than hydrogen and helium. Globular cluster stars contain very low abundances of carbon, oxygen, iron, and other heavy elements because they formed before many generations of supernovae had enriched the galaxy with these elements. This chemical signature confirms their great age. When these stars formed, the universe consisted almost entirely of hydrogen and helium left over from the Big Bang, plus tiny amounts of lithium and beryllium. All heavier elements have been created inside stars and dispersed by supernovae. The metal-poor composition of globular clusters is a fossil record of the early universe, preserved in stellar atmospheres for billions of years. The Milky Way has approximately 150 globular clusters that we know of, though there may be more hidden behind dust clouds or too faint to detect. They are distributed in a roughly spherical halo, extending up to 200,000 light-years from the galactic center, well beyond the visible disk. Each cluster follows its own independent orbit around the galaxy, sometimes plunging through the disk, sometimes reaching out to enormous distances before falling back in. The orbital periods of these clusters can exceed 1 billion years for the most distant ones. They are time capsules in motion, each one carrying information about the conditions that existed when our galaxy was young, each one a survivor from an era when the universe itself was in its infancy. In addition to globular clusters, the halo contains individual stars following similar highly elliptical orbits. These are called halo stars. Some were likely stripped from globular clusters by tidal forces as the clusters passed through the dense galactic disk. Others may have formed independently in the early halo. Like globular cluster stars, halo stars are metal poor and ancient. They move through the galaxy on orbits that are not aligned with the disk's rotation, sometimes even orbiting retrograde, opposite to the direction of most stars. When a halo star passes through our neighborhood, it stands out like a time traveler from the distant past, a visitor from an earlier epoch of galactic history moving through a younger stellar population with different chemical composition and different orbital dynamics. The stellar halo tells us about the Milky Way's formation. Current models suggest the galaxy formed from the merger of smaller proto-galaxies in the early universe. These smaller systems collided and merged, their stars mixing together but retaining some memory of their original orbits. The globular clusters and halo stars we see today are remnants of these early building blocks. By studying the properties of different stellar populations in the halo, astronomers can reconstruct the merger history of the Milky Way, identifying which clusters and stars likely came from which protogalaxy. In a sense, the halo is an archaeological site, and each star is an artifact waiting to reveal information about our galaxy's deep past. The story written in the halo is one of collision, merger, and gradual assembly over billions of years. As we prepare to leave the stellar halo, let us appreciate what these ancient structures represent. The globular clusters and halo stars are survivors. They formed in an era of intense stellar birth when galaxies were colliding frequently and the universe was filled with the light of young stars. They have orbited our galaxy for 12 billion years or more, witnessing the entire evolution of the Milky Way from its chaotic youth to its mature present. They have survived countless passages through the galactic disk, gravitational encounters with giant molecular clouds, and the slow erosion of tidal forces. They are the oldest things we can observe in our galaxy, older even than our Sun by more than 7 billion years. They remind us that the universe has a history, a deep past stretching back nearly to the beginning of time itself. And they continue their patient orbits, ancient guardians watching over the galaxy that shaped them and which they helped to build. We now approach one of the deepest mysteries in astronomy. Everything we have discussed so far, the stars, nebulae, globular clusters, and supermassive black hole, all of this luminous matter accounts for less than 15% of the Milky Way's total mass. The remaining 85% or more is composed of something we cannot see, something that does not emit or absorb light, something that interacts with ordinary matter only through gravity. This is dark matter, and it fundamentally shapes the structure and evolution of our galaxy. For the next several minutes, we will explore this invisible component, understand how we know it exists, and contemplate what it means for our understanding of the universe. We are about to discuss something that makes up most of the galaxy's mass, yet remains completely invisible to our eyes. The evidence for dark matter comes from multiple independent observations, all pointing to the same conclusion. When astronomers measure the orbital velocities of stars in the outer regions of the galaxy, they find something unexpected. According to Newton's laws and Einstein's general relativity, stars farther from the galactic center should orbit more slowly, just as outer planets in our solar system orbit more slowly than inner planets. But this is not what we observe. Stars in the outer galaxy orbit at roughly the same speed as stars closer to the center, sometimes even faster. This flat rotation curve, as it is called, can only be explained if there is additional mass beyond what we can see, mass that does not decrease with distance from the center, but instead extends in a large spherical halo around the visible galaxy. Additional evidence comes from gravitational lensing, the bending of light by massive objects. When we observe distant galaxies being lensed by foreground galaxy clusters, the amount of bending tells us the total mass of the lensing cluster. The mass required to produce the observed lensing is always much greater than the mass we can account for by adding up all the visible stars and gas. Dark matter is necessary to explain the lensing. Yet more evidence comes from the cosmic microwave background, the afterglow of the Big Bang. Tiny fluctuations in this ancient light carry information about the matter content of the universe, and the patterns we observe can only be explained if most of the matter is dark. From galactic scales to cosmological scales, from multiple independent techniques, the evidence all points to the same conclusion. Dark matter is real, and it is everywhere. What is dark matter made of? This is one of the most important unsolved problems in physics. We know what it is not. It is not ordinary matter that simply fails to emit light. There is not enough room in the universe for that much ordinary matter without violating multiple observational constraints. Dark matter must be something fundamentally different, likely a particle or particles not yet discovered in laboratory experiments. The leading candidate is a class of particles called WIMPs, weakly interacting massive particles. These would be massive enough to account for the observed gravitational effects, but would interact so weakly with ordinary matter that they could pass through the Earth without ever colliding with a single atom. Thousands of scientists are currently searching for dark matter particles using incredibly sensitive detectors buried deep underground to shield them from cosmic rays. So far, dark matter has eluded direct detection. The dark matter halo of the Milky Way extends well beyond the visible disk, perhaps out to 600,000 light-years or more from the galactic center. If we could see dark matter, the Milky Way would appear not as a flat disk, but as an enormous sphere with the visible galaxy embedded in its center, like a fried egg suspended in a much larger ball of gelatin. This dark matter halo is not uniformly distributed. Computer simulations suggest it should contain substructure, clumps, and streams of dark matter that are remnants of smaller dark matter halos that merged with the Milky Way over time. Some of these dark matter subhalos might even host their own small galaxies, too faint for us to detect. The dark matter distribution is complex, shaped by billions of years of gravitational interactions and mergers. Without dark matter, the Milky Way as we know it could not exist. The visible matter alone does not have enough gravity to hold the galaxy together at its observed rotation speeds. Stars in the outer regions would be flung into intergalactic space. The galaxy would disperse over time. Dark matter provides the gravitational glue that holds everything together. It also played a crucial role in galaxy formation itself. In the early universe, dark matter began collapsing into clumps before ordinary matter did, because dark matter does not interact with radiation and could therefore begin collapsing earlier. These dark matter clumps created gravitational wells into which ordinary matter fell, eventually forming the galaxies we observe today. In a very real sense, dark matter is the foundation upon which all galactic structure is built. The visible galaxies are just the icing on a much larger dark matter cake. The existence of dark matter has profound philosophical implications. It means that most of the mass in the universe is composed of something fundamentally different from the atoms that make up our bodies, our planet, and all the stars we see. We are the minority component. The universe is dominated by a substance we do not yet understand. This should be humbling. For most of human history, we believed we understood the basic nature of matter. We built a periodic table of elements, understood atomic structure, and could explain the properties of materials in terms of atoms and molecules. Now we know that all of this, all of chemistry and atomic physics, applies only to the small fraction of the universe's mass that is ordinary matter. The majority of the cosmos is dark, invisible, and mysterious. We are still just beginning to understand the universe we inhabit. As we contemplate the dark matter halo enveloping our galaxy, we might feel both insignificant and privileged. We are embedded in a structure far larger and more massive than what we can see, shaped by forces we are only beginning to understand. Yet we are also fortunate to live in an era when technology and human ingenuity have advanced to the point where we can detect this invisible component, map its distribution, and begin to understand its properties. A century ago, we did not know dark matter existed. A century from now, we will likely have identified its nature and perhaps even learned to detect it directly. We are living through a golden age of discovery, watching as one of the universe's greatest mysteries gradually yields its secrets. The dark matter halo is not just a scientific curiosity. It is a reminder of how much we have yet to learn and how exciting the quest for knowledge remains. The Milky Way is not a static structure. It is dynamic, evolving, constantly in motion. Every star follows its own orbit around the galactic center, creating complex patterns of motion that play out over millions and billions of years. For the next several minutes, we will explore the concept of galactic motion and time, understanding how the galaxy rotates, how stars move within it, and what changes occur over the vast timescales of galactic evolution. Just as Earth experiences seasons as it orbits the Sun, perhaps the galaxy experiences its own slow seasons as it evolves through cosmic time. Come with me now as we explore the dance of time and motion that shapes our galactic home. The Sun orbits the galactic center once every approximately 225 million years. This period, sometimes called a galactic year or a cosmic year, is the fundamental time unit for galactic processes. During one galactic year, the Sun travels a distance of roughly 900,000 light years, moving at about 220 kilometers per second relative to the galactic center. To put this in perspective, the last time Earth was at its current position in its galactic orbit, the supercontinent Pangaea was just beginning to form, and mammal-like reptiles were the dominant land animals. The next time Earth completes a full galactic orbit, who knows what species, if any, will inhabit our planet. Galactic years are almost incomprehensibly long by human standards, yet they are the natural timescale for galaxy evolution. As the Sun orbits, it also oscillates up and down through the galactic plane, like a horse on a carousel that moves up and down as the carousel spins. This vertical motion has a period of about 60 to 70 million years. Currently, the Sun is close to the midplane of the galaxy, but in about 30 million years it will reach its maximum height above the plane before falling back down. Some researchers have suggested that mass extinctions on Earth might correlate with these passages through the plane when the solar system encounters denser regions of molecular clouds and dust. The evidence remains debated, but the possibility reminds us that our motion through the galaxy may have consequences for life on Earth. We are not isolated from galactic processes. We are embedded in them, affected by them, part of the larger cosmic environment. The galaxy's differential rotation means that stellar orbits are not simple circles. Stars at different radii orbit at different speeds, causing the disk to shear and stretch over time. This shearing motion is responsible for winding up the spiral arms, though, as we learned earlier, density waves allow the arms to persist despite this winding. The differential rotation also means that stars that form together in the same molecular cloud gradually drift apart over time. After a few 100 million years, the sibling stars are scattered along the galaxy's disk, their common origin evident only through careful chemical analysis showing they have identical elemental abundances. The galaxy mixes and remixes its stellar population, erasing most evidence of where and when stars formed, creating a thoroughly blended population of stars of all ages and compositions. The Milky Way is also slowly changing its overall structure. The central bar may be relatively young, perhaps only a few billion years old, and it may eventually dissolve as orbital resonances change. The spiral arms are not permanent features, but patterns that come and go over hundreds of millions of years. Interactions with satellite galaxies can trigger new spiral arm formation or disrupt existing arms. The galaxy is eating smaller galaxies, slowly growing larger as it consumes its neighbors. On very long timescales, the Milky Way is evolving, its appearance today different from its appearance billions of years ago and different from what it will look like billions of years in the future. If we could watch the galaxy evolve in fast forward over its entire lifetime, we would see it change shape, merge with neighbors, form and dissolve structures, a living system constantly transforming. The rate of star formation in the Milky Way has decreased over time. In the early universe, when gas was more abundant and galaxies were colliding more frequently, star formation rates were much higher than today. The galaxy was brighter, bluer, more active. Now, in its mature phase, star formation continues, but at a more sedate pace. The galaxy is aging, slowly exhausting its gas supply. Eventually, billions of years from now, the Milky Way will run out of gas entirely and star formation will cease. The galaxy will gradually redden as its massive blue stars die off and only long-lived red dwarf stars remain. It will become a red and dead elliptical galaxy, a quiet stellar graveyard where nothing new happens. But that fate is still many billions of years away. For now, the Milky Way remains vibrant and alive. Perhaps the most dramatic event in the Milky Way's future is its eventual collision with the Andromeda Galaxy. Andromeda, our nearest large galactic neighbor, is currently approaching us at about 110 kilometers per second. In approximately 4 to 5 billion years, the two galaxies will collide. This will not be a collision in the sense of stars crashing into each other. Space is so empty that even when galaxies merge, individual stars almost never collide. Instead, the two galaxies will pass through each other, their gravitational fields disrupting each other's structure. After a few passes, they will eventually merge into a single, larger elliptical galaxy that astronomers have already nicknamed Milkometa. The night sky from Earth, if Earth still exists then, will be spectacular during the merger, with the Andromeda Galaxy filling the sky like a brilliant second Milky Way before the two systems blend together. As we reflect on galactic time and motion, we must acknowledge the humbling perspective it provides. All of human history, all of recorded civilization, spans less than 1/100% of a single galactic year. On the timescale of galactic evolution, human civilization is a fleeting instant, a blink of an eye. The galaxy was here long before us and will be here long after us. It is easy to feel insignificant in the face of such vastness. Yet we are also remarkable. We are pattern-making machines, storytelling apes who have figured out how to understand the galaxy's structure, motion, and evolution. We have learned to see the invisible, to hear the inaudible, to comprehend the incomprehensible. The galaxy may be vast and ancient, but we are the part of it that has become aware, that wonders and questions and seeks to understand. That awareness is precious and worth celebrating. The Milky Way does not exist in isolation. It is part of a small cluster of galaxies called the Local Group, containing more than 50 galaxies bound together by their mutual gravity. For the next several minutes, we will zoom out from our galaxy and explore this larger neighborhood, meeting our galactic neighbors and understanding how they interact with the Milky Way. These neighboring galaxies are not just distant objects. They are companions on a cosmic journey, and their gravitational dance with the Milky Way has shaped both our galaxy and theirs over billions of years. Come with me now as we explore the Local Group, our extended galactic family. The dominant member of the Local Group, aside from the Milky Way, is the Andromeda Galaxy, also known as M31. Andromeda is a massive spiral galaxy similar to our own, containing perhaps 1 trillion stars compared to our few 100 billion. It lies about 2.5 million light-years away, making it one of the most distant objects visible to the naked eye. When you look at Andromeda in the night sky, you are seeing light that left that galaxy when early humans were just beginning to walk upright on the plains of Africa. Andromeda is both similar to and different from the Milky Way. It has spiral arms and a central bulge, but its stellar population and history are distinct. Studying Andromeda gives us insights into what the Milky Way might look like from outside, as it is the closest major galaxy comparable to our own. The third major member of the local group is the Triangulum Galaxy, M33, a smaller spiral galaxy lying about 3 million light-years from Earth. Triangulum contains perhaps 40 billion stars, making it much smaller than either the Milky Way or Andromeda. Unlike our two galaxies, Triangulum does not have a prominent central bulge, giving it a more delicate, ethereal appearance. Some astronomers believe Triangulum may be a satellite of Andromeda, bound to orbit around it rather than being a completely independent galaxy. Triangulum is important because it is the most distant object easily visible to the naked eye under very dark skies, and because it represents the kind of smaller spiral galaxy that is actually more common in the universe than massive ones like the Milky Way and Andromeda. Orbiting the Milky Way are dozens of smaller satellite galaxies, gravitationally bound companions that circle our galaxy like moons orbiting a planet. The two most prominent are the Large and Small Magellanic Clouds, visible as fuzzy patches in the southern hemisphere sky. These irregular dwarf galaxies lie about 160,000 and 200,000 light-years away, respectively. They are star-forming systems containing billions of stars and large amounts of gas. The gravitational interaction between the Magellanic Clouds and the Milky Way is pulling streams of gas off the smaller galaxies, gas that will eventually fall into the Milky Way and fuel new star formation. In this way, our galaxy is slowly consuming its satellites, growing larger by cannibalizing smaller neighbors. It is a violent process, but it is how large galaxies like the Milky Way grow over time. Most of the satellite galaxies orbiting the Milky Way are much fainter than the Magellanic Clouds. These ultra-faint dwarf galaxies contain only a few thousand to a few million stars, making them incredibly dim and difficult to detect. Many have been discovered only in the last few decades, as digital surveys of the sky have become sensitive enough to pick them out against the background of Milky Way stars. These tiny galaxies are important for several reasons. They are among the most dark matter-dominated objects in the universe, with ratios of dark matter to ordinary matter that can exceed 1,000 to 1. They are also among the oldest galaxies, fossil remnants from the early universe that have somehow survived until today without merging into larger systems. Studying them gives us insights into galaxy formation in the early cosmos. The local group is bound together by gravity and is isolated from other galaxy groups. The nearest large galaxy cluster, the Virgo cluster, lies about 50 million light-years away. In the space between the local group and Virgo, there are other small galaxy groups and isolated galaxies, but the overall density of galaxies is much lower than within clusters. This isolation means the local group is relatively quiet. There are no major ongoing mergers aside from the Milky Way slowly consuming its satellites, and the main event in our future is the eventual collision with Andromeda billions of years from now. The local group represents a typical environment for galaxies in the universe. Most galaxies live in small groups like ours rather than in giant clusters, making the local group a good laboratory for understanding galaxy evolution. Andromeda also has its own system of satellite galaxies, perhaps even more extensive than the Milky Way's. When the two galaxies eventually merge, their satellite systems will also merge, creating an even richer system of dwarf galaxies orbiting the combined Milky galaxy. Some of these satellites may be disrupted during the merger, their stars scattered into long tidal streams. Others may survive and continue orbiting the merged galaxy. The merger will be chaotic, but eventually a new equilibrium will be reached. The future local group will be dominated by one giant elliptical galaxy surrounded by a scattered population of smaller satellites, a very different configuration from what we see today. But again, this is billions of years in the future. For now, the local group remains a relatively peaceful neighborhood of galaxies, each following its own orbit through space, each with its own history and character. As we contemplate the local group, we gain perspective on the Milky Way's place in the universe. Our galaxy is not the largest or most massive in even this small corner of the cosmos. It is one of two dominant members sharing the gravitational stage with Andromeda. Yet it is also enormous compared to most of the local group's members, which are tiny dwarf galaxies barely visible even with powerful telescopes. The local group reminds us that the universe is hierarchical. Planets orbit stars, stars orbit galaxies, galaxies cluster together in groups, and groups are drawn toward larger clusters. The Milky Way exists within this cosmic hierarchy, neither at the center nor at the periphery, but somewhere in the middle scales of structure. Understanding our galactic neighborhood helps us understand where we fit in the grand architecture of the universe. We now take our final outward journey, zooming back from the local group to see the Milky Way in its largest context. If we could travel far enough and fast enough to view the universe on truly cosmic scales, we would discover that galaxies are not randomly scattered through space. They are organized into an intricate structure called the cosmic web, a vast network of filaments, walls, and voids that spans the observable universe. For the next several minutes, we will explore this larger scale of structure, understanding how the Milky Way fits into the grand architecture of the cosmos. This is the ultimate perspective, the view from which even galaxies become mere points of light arranged in patterns of breathtaking complexity and beauty. The cosmic web formed from tiny density fluctuations in the very early universe, fluctuations imprinted during the inflationary epoch moments after the Big Bang. These slight variations in density grew over time under the influence of gravity. Regions that were slightly denser attracted more matter, becoming even denser. Regions that were slightly less dense lost matter to their denser neighbors, becoming voids. Over billions of years, this process created the structure we see today. Dark matter played a crucial role in this process. Because it interacts only through gravity and is unaffected by radiation, dark matter could begin collapsing earlier than ordinary matter, creating the gravitational scaffolding around which ordinary matter eventually gathered. The cosmic web is fundamentally a dark matter structure, with galaxies marking the densest regions where ordinary matter has accumulated. The local group resides within a relatively quiet region of the cosmic web, not in a major filament, but in a bridge between larger structures. Our nearest massive structure is the Virgo cluster, containing thousands of galaxies bound together in a single gravitational system. The Virgo cluster lies at the heart of the Virgo supercluster, a larger collection of galaxy groups and clusters that includes the local group. Even the Virgo supercluster is part of a still larger structure called Laniakea, a supercluster of superclusters containing over 100,000 galaxies. The Milky Way is just one galaxy in the local group, which is just one group in the Virgo supercluster, which is just one region of Laniakea, which is just one structure among countless others filling the observable universe. The scales become almost absurd, yet they are real. The voids between filaments are not completely empty, but they are extraordinarily underdense compared to the filaments and clusters. A void might contain a few scattered dwarf galaxies and little else across volumes hundreds of millions of light years across. If you lived in a galaxy within a void, your night sky would be hauntingly empty. You might see only a handful of faint neighboring galaxies, and the cosmic web itself would be invisible, visible only through detailed surveys revealing the distant filaments on the horizon of your observable universe. Life in a void would provide a very different perspective on the cosmos, one of isolation and emptiness rather than the richness we experience in our relatively well-connected corner of the universe. The voids remind us that most of space is truly empty, and galaxies are rare, special things concentrated in a tiny fraction of cosmic volume. The largest structures in the universe are the filaments themselves, stretching for hundreds of millions of light years and containing thousands of galaxies strung along their length like pearls on a cosmic string. Where filaments intersect, galaxy clusters form at the nodes. These clusters are the most massive gravitationally bound structures in the universe, containing thousands of galaxies, vast quantities of hot intracluster gas, and enormous amounts of dark matter. The largest clusters can have total masses exceeding 1 million billion times the mass of the Sun. They are cosmic cities, dense concentrations of galaxies interacting gravitationally, sometimes merging, their evolution driven by the tremendous gravitational forces at play in such massive systems. The Milky Way, as a member of a small group rather than a massive cluster, has experienced a relatively calm existence by comparison. The cosmic web is not static. All structures within it are in motion, drawn by gravitational attractions toward the densest regions. The local group, including the Milky Way, is falling toward the Virgo cluster at a speed of several hundred kilometers per second. The Virgo cluster itself is falling toward even larger concentrations of matter. This cosmic flow represents the ongoing collapse of structure in the universe as gravity continues to pull matter from less dense regions toward denser ones. Eventually, many billions of years from now, local structures will merge into ever larger gravitationally bound systems. But on the very largest scales, the expansion of the universe will ultimately win. Structures separated by more than about 300 million light-years will recede from each other faster and faster as dark energy drives the accelerating expansion of space itself. When we view the cosmic web, we are seeing the largest patterns created by gravity in the universe. On scales larger than about 1 billion light-years, the universe begins to look statistically uniform in all directions. This is the cosmological principle in action. There is no center to the cosmic web, no special location. Every observer in every galaxy would see themselves surrounded by a cosmic web of similar statistical properties. The Milky Way's location is not special or privileged. We occupy a typical position in a typical galaxy group in a typical region of the cosmic web. This should be both humbling and comforting. We are not the center of anything, but we are also not uniquely isolated or disadvantaged. We are part of the grand pattern, neither more nor less significant than countless other galaxies scattered across the observable universe. As we contemplate the cosmic web, we must acknowledge that what we see is only a small fraction of what exists. The observable universe extends about 46 billion light-years in all directions, encompassing everything from which light has had time to reach us since the Big Bang. But the universe beyond our observable horizon almost certainly extends much farther, perhaps infinitely. The cosmic web we can map is just the tiny local region of a structure that may have no edge and no end. We are like cartographers on a small island who have just learned the ocean exists but have no idea how large it might be. The humility this perspective provides is valuable. We know so much more than our ancestors about the structure of the cosmos, yet we remain profoundly ignorant of the true extent and nature of reality. The journey of discovery continues with no end in sight. We have journeyed far from our starting point. We have explored the galactic center with its supermassive black hole, witnessed the birth of stars in stellar nurseries, traced the graceful spiral arms, met our galactic neighbors, and zoomed out to see the cosmic web itself. Now it is time to return home, to bring our perspective back to Earth and reflect on what it means to be a small planet orbiting a modest star in the quiet suburbs of the Milky Way. For these final minutes together, we will contemplate our place in the cosmos and what the Milky Way teaches us about ourselves. This is where knowledge becomes wisdom, where astronomy becomes philosophy, where the facts we have learned transform into meaning. From our journey, we have learned that the Milky Way is both ordinary and extraordinary. It is an ordinary barred spiral galaxy, one of hundreds of billions in the observable universe. Its structure, composition, and evolution follow patterns we see in countless other galaxies. There is nothing unique about the Milky Way on cosmic scales, yet it is also extraordinary because it is ours. It is the galaxy that birthed our sun, that provided the heavy elements necessary for rocky planets and biological life, that created the stable environment in which intelligence could evolve. Every atom in your body was forged in stars belonging to this galaxy or its predecessors. Your existence is intimately tied to the Milky Way's history and evolution. You are not just in the galaxy. You are of the galaxy, a temporary pattern in the endless recycling of matter and energy. The Milky Way teaches us about time and scale in ways that can transform our daily perspective. When you feel stressed about deadlines and worried about the future, remember that the galaxy has been here for 13 billion years and will continue for billions more. The concerns that loom so large in human affairs are fleeting moments in cosmic time. This is not to diminish the importance of human experience, but rather to provide context. We exist in the present moment, but that moment is part of an unbroken chain stretching back to the origin of the universe itself. Every moment is simultaneously insignificant and precious. We are temporary, but we are also participants in something eternal, the ongoing evolution of matter and energy in the cosmos. The galaxy also teaches us about connection and interdependence. No star exists in isolation. Every star is gravitationally connected to every other star in the galaxy. The motion of one affects, however slightly, the motion of all others. The elements created in one generation of stars become the raw materials for the next generation. Supernova explosions trigger new star formation. Black holes shape their galactic environments. Everything is connected in an intricate web of cause and effect playing out over cosmic timescales. This interconnectedness mirrors the interconnectedness of life on Earth. We tend to see ourselves as separate individuals, but we are part of biological and social systems every bit as complex and interdependent as the galaxy itself. The atoms of your body have been part of countless other organisms over Earth's history. In this very literal sense, you are connected to everything that has ever lived. Perhaps the most profound lesson the Milky Way offers is about perspective. From Earth, the stars appear fixed and eternal, unchanging from night to night and year to year. But we have learned that this is an illusion created by the vast timescales involved. The galaxy is dynamic, constantly changing, evolving, transforming. Stars are born and die. Spiral arms form and dissolve. The entire structure rotates and evolves. Nothing is permanent. Changes. This truth applies not just to galaxies, but to all levels of existence. Resisting change is futile. Embracing change, flowing with it, understanding that impermanence is the nature of reality. This is wisdom. The galaxy, in its patient evolution over billions of years, models this wisdom. It does not resist its own transformation. It simply unfolds according to the laws of physics, creating beauty in the process. The fact that we can understand the galaxy at all is itself profound. We are made of atoms forged in stars, yet we have developed the capacity to understand those stars and the galaxy they compose. We are the universe, examining itself, matter that has become conscious and curious about its own origins. This self-awareness is rare and precious. As far as we know, it may be unique to Earth, though the galaxy is vast and surely contains other worlds where consciousness has emerged. But whether we are alone or one among many, the fact that consciousness exists at all, that the universe has developed the capacity to contemplate itself, is miraculous. You, reading these words or hearing this narration, are a temporary configuration of atoms that has somehow developed the ability to wonder about galaxies. That is extraordinary. The Milky Way is our home in the deepest sense. Earth is our immediate home, the solar system, our neighborhood, but the galaxy is our larger context, the system that has shaped us and continues to influence us in countless subtle ways. When you look up at the night sky and see the Milky Way band stretching overhead, you are seeing your home from inside. You are looking at the galaxy that created you, that sustains the stable environment necessary for your existence, that will continue long after you and everyone you know has returned to stardust. This should evoke both humility and gratitude. Humility, because we are so small and temporary in the cosmic scheme. Gratitude, because we have been given, by chance and by the laws of physics, this brief opportunity to exist, to experience, to understand. What we do with this opportunity is up to us. As we conclude our journey through the Milky Way, I invite you to carry this perspective with you. When the concerns of daily life feel overwhelming, step outside on a clear night and look up. Remember that you are standing on a planet orbiting a star in the quiet suburbs of a vast galaxy containing hundreds of billions of other stars. Remember that the light you see from the Milky Way left those stars thousands of years ago and has been traveling through space to reach your eyes at this moment. Remember that you are made of elements created in stellar furnaces, that you are a child of the cosmos, that your existence is a temporary but precious manifestation of the universe's creative power. Let this perspective bring you peace, wonder, and a sense of connection to something far greater than yourself. The Milky Way has been here for 13 billion years, patiently creating the conditions for life and consciousness to emerge. You are part of that story. You are the galaxy's way of knowing itself. And that is beautiful beyond words. Thank you for joining me on this journey through our home galaxy. I hope these images and this perspective bring you peace tonight and in the nights to come. Remember that whenever you feel lost or overwhelmed, the stars are still there, the galaxy still turns, and you are part of something infinitely larger and more beautiful than any temporary concern. If you found peace or wonder in this journey, consider sharing it with someone else who might benefit from this cosmic perspective. And remember, you are made of stardust. You are a way for the cosmos to know itself, and you are home. Sleep well, fellow traveler. The Milky Way will be here when you wake, as it has been for billions of years, as it will be for billions more. You are exactly where you need to be.